Robert Crawford again, and I am back with the ARC4500A's Week 10 lecture. This week we will be going over environmental analysis and performance-based design. So let's jump right into it. Why is environmental analysis important in our industry? Well, simply put, as you can see in this graphic between building operations and building materials and construction, buildings generate nearly 40% of the annual greenhouse gas emissions, and approximately 2/3 of the building square footage that exists today will still exist in 2050. So the problems we have with the building stock today aren't going away anytime soon. Environmental analysis is a broad topic, so I thought it might be good to provide a little bit of context as to some of the rating systems that are out there, and either directly related to or tangentially related to better understanding the impact we have on the environment. The current population of the world is nearing 8 trillion people, and by 2060, it is projected to approach 10 trillion people. Some scientists actually project 10 trillion people as the limit of what the Earth can sustain. Unsurprisingly, given this population growth, the amount of building square footage will also continue to go up. But surprisingly, at a much faster clip, it is expected to double between now and 2060. Embodied carbon is 1/4 of annual building sector emissions and growing. As operational energy efficiency increases, the impact of embodied carbon emissions in buildings will become increasingly significant. You might be wondering, what exactly is the difference between embodied carbon and operational carbon? Sean Lockey of Faithful Gould notes operational carbon refers to carbon dioxide emitted during the life of a building from the regulated and unregulated loads associated with the use of a building. This includes the emissions from, say, the heating, cooling, lighting, and ICT. Embodied carbon, however, refers to carbon dioxide emitted during the manufacture, transport, construction of building materials, together with end-of-life emissions. So, for example, if you are specifying concrete on a project, then carbon will have been emitted making that concrete. Those emissions occur during extraction of the raw materials, aka the cradle, processing in a factory, transporting the concrete to a construction site, etc. This we refer to as the embodied carbon. The increase in population and new construction will also involve an increase in construction waste. Adam Redlin notes, a new report by Transparency Market Research forecasts that the global volume of construction debris is set to balloon in the coming years. Construction debris is anything that is generated as a result of construction and then abandoned, regardless of whether it has been processed or stockpiled. According to a report by the World Bank in 2012, there is a global collective of 1.3 billion tons of solid waste every year. This volume is expected to increase to 2.2 billion tons every year by 2025. Building material accounts for half of the solid waste generated every year worldwide. If you ever wondered about where does all that trash go once it's been thrown out, does it simply go to a waste facility in the nearby town, or do people reuse it? How does it get reused? Well, MIT wondered that same question, and their Sensible City lab created these sensors. They attached them to pieces of trash and just watched the data unfold. This video is pretty amazing, so I suggest you click on the YouTube link at the bottom of this slide when you have a moment. So what is being done to address these issues? Well, for one, building codes are starting to tackle energy efficiency and are becoming increasingly ambitious with what they require. California has adopted some of the most progressive energy and green building codes in the country. As a quick primer to the California Building Standards Code, which is the building code for California in Title 24 of the California Code of Regulations, it consists of 12 parts. Part 1, California Building Standards Administrative Code. Part 2, the California Building Code. This covers a variety of topics from fire life safety to structural design to accessibility for both residential and non-residential. Residential is covered in Part 2.5. Part 3, the California Electrical Code. Part 4, the Mechanical Code. Part 5, the Plumbing Code. Part 6 is the Energy Code. 7 we can skip, which is vacant. 8, the Historical Building Code. 9, the Fire Code. 10, the Existing Building Code. And 11, the Green Building Standards Code, which lays out a series of mandatory and non-mandatory measures that cover items like long and short-term bicycle parking, clean air vehicle parking, electrical charging station requirements, fireplace ventilation, water efficiency of fixtures and material conservation, and generally resource efficiencies. Part 12 is the California Reference Standards Code, and that covers those 12 parts. With respect to environmental analysis, we will look primarily at the California Energy Code, or Part 6. As a quick aside, many people mistakenly refer to this part of Title 24 as T24. When you hear someone say T24 calculations, they are really referring to the calculations required in Part 6 of Title 24. Title 24 refers to all 12 parts of the California Building Standards Code, but no need to get hung up on that. A little bit of history. The California Energy Code was created by the California Building Standards Commission in 1978 as a response to a legislative mandate to reduce California's energy consumption. So has that strict energy code worked? David Roberts of Vox writes, California boosters often note that the state has become more energy efficient than the rest of the U.S., which has helped keep its residents' energy bills low even as the per-unit cost of energy increases. Skeptics have said that the state is merely taking credit for the effects of a temperate climate and copious natural resources, including hydroelectric power. Oddly, no one seems to have run the numbers on it to figure out whether California really is a leader or if it's just lucky. But now, in a report of the Natural Resources Defense Council, Ralph Kavanaugh, Peter Miller, and Charlie Komanoff gathered the official statistics, made the spreadsheet, and dug into the question of whether California really is doing something right. The answer, yes it is. California is decreasing its energy intensity, energy consumed per unit of GDP, and its carbon intensity, carbon emissions per unit GDP. In fact, if the rest of the nation had improved as quickly as California has between 1975 and 2016, U.S. greenhouse gases would be almost 25% lower, NRDC found. And this improvement in performance has not come at the expense of economic growth. Instead, it's been a huge factor in the state's economic boom. Over the past 40 years, its population and economy have grown faster than the rest of the U.S. Feel free to check out the report for yourself. Just click on the link in the slide deck. Taking a closer look at Part 6, it not only requires a building meet a specific level of energy performance, it allows for that to be met prescriptively or via a performance-based method. We will get into what that means more precisely later in the lecture. If one elects to pursue the performance avenue, an energy model is required to validate the anticipated performance of the building. Part 6 actually identifies specific software which is acceptable to use to perform those calculations. First, the California Building Energy Code Compliance for Commercial, or CBECC, which is compatible with SketchUp. Second, Integrated Environmental Solutions Virtual Environment, or IESVE, which has plugins for Revit and SketchUp. And third, EnergySoft's Energy Pro. Outside of code, you might be wondering what other programs exist to help provide a framework by which to judge and incentivize the creation of more sustainable buildings. You've likely heard of LEED, or Leadership in Energy and Environmental Design, but there are several other rating systems that have recently come online. The Building Research Establishment Environmental Assessment Methodology is another rating system which is popular in the UK and is actually older than LEED. You may also know that LEED has a rating system specific to buildings, the BD+C, which stands for Building Design and Construction. One can also achieve a LEED certification specific to a project for interior design and construction, building operations and maintenance, neighborhood development, homes, and cities and communities. The U.S. Green Building Council, which developed LEED, also has under its umbrella SITES, Total Resource Use and Efficiency, TRUE, ParkSmart, EDGE, WELL, which is a performance-based system for measuring buildings' features that impact human well-being. It aims to improve the way people live by furthering spaces that enhance occupant health and quality of life. Eric Dolan Del Vecchio describes the primary difference between the two systems, BREEAM and LEED, as BREEAM has licensed assessors who examine the evidence against credit criteria and report it to BREEAM's parent company, Building Research Establishment, BRE. BRE then assesses the report and issues the certificate if they feel it meets the requirements. LEED, on the other hand, does not collect the evidence. The design team does. They then send the data to the USGBC, who examines it and issues a certificate if it meets their demands. Green Globes is an online green building rating and certification tool that is used primarily in Canada and the USA. BOMA is perhaps best known for their floor measurement standards, but they also offer BOMA 360 Performance Program, which evaluates buildings against industry best practices in 6 areas: building operations and management, security risk management, life safety, training and education, energy, environmental sustainability, tenant relations, and community involvement. Energy Star is a government-backed program providing easy-to-use tools to promote energy efficiency. The Living Building Challenge, launched in 2006, is self-described as a philosophy, certification, and advocacy tool for projects to move beyond merely being less bad and to become truly regenerative. In terms of a good overall introduction to environmental analysis and energy modeling, the AIA has actually put together a decent guide. It is a bit long, 86 pages, so I am not asking you to read all of this, but if it interests you, it touches upon the relationship of energy modeling to codes and its use as a design tool, what might be good to accomplish at what stage of the design process, from concept design to SD, DD, and CDs, and definitions of key terms like energy use intensity, aka EUI, and how what is modeled does not always match what is measured and why. Please feel free to peruse this at your leisure. Let's next take a look at some of the more common analysis tools we have at our disposal. Sapphira is a popular software that works with Revit and SketchUp. It provides interactive building performance feedback through its Sapphira architecture plugin, which calculates and graphically displays metrics including daylight factors, energy use intensity, and energy use breakdown by building system in real time on a performance dashboard. Here is a view of its daylight visualization tool, which shows the distribution of natural light throughout the building. Similarly, the direct sunlight analysis tool quantifies the amount of direct sunlight each space receives throughout the day, a metric used in certification programs such as Australia's SETP 65 program and the BREEAM system. Sapphira's web app, which uses the cloud to process and analyze models with the Energy Plus simulation engine, provides a faster and more in-depth analysis of the building model while allowing for straightforward comparisons between design options. Students and educators are able to utilize Sapphira for free so long as it is not utilized for commercial purposes. If you are curious to test this out on your SketchUp or Revit models, I encourage you to download the plugin and experiment with it. You can learn more about how to use the plugin by watching their YouTube videos. The link for that is included in the bottom of this slide. Next, we will take a look at using Revit's built-in energy analysis modeler, which is called Autodesk Insight. First things first, you will need to install the Insight add-in and set up a login/account. Similar to Sapphira, this should be free of charge as long as you are a student using it for non-commercial purposes and adhere to any other terms of service. Please pause here and do so prior to proceeding with the video. Click the link in the slide deck to set this up. Great. Now that we have Insight installed, you should see the Insight features under the Analyze tab, as you can see here in this image. Heating and cooling, lighting, and solar analysis functions are now available to us. Those tools can be used at a variety of stages of development, from concept design to SD, DD, etc. They are, of course, most impactful earliest in the design process, so let's test them out on a simple conceptual mass. Feel free to rewind a few weeks if you need to refresh yourself on how to create a conceptual mass and the different ways in which we can create those forms. Here, I have created a simple one. Added levels, selected my mass, selected the mask floors button, and then automatically created mask floors within that mass at each level. And then using those mask floors, I've created floor elements from those, resulting in something that looks like the image in the lower right. Now that our conceptual mass is created, we will go back to the Analyze tab and click on Location, and then just type in the address of your project site and click OK to set it. Next up, you will click Create Energy Model, and you will be warned this can take a little while to process. So now might be a good time to pause and grab a snack. A little while later, you should receive an automated email similar to this, noting your insight is ready to be viewed. Click on the link and you will be taken to the Insight dashboard, where a number of features can be assessed or viewed outside of Revit. The first one you might notice is the benchmark against ASHRAE 90.1 and Architecture 2030. What exactly are those? ASHRAE stands for the American Society of Heating, Refrigerating, and Air Conditioning Engineers. ASHRAE Standard 90.1 has been a benchmark for commercial building energy codes in the United States and a key basis for codes and standards around the world for more than 35 years. ASHRAE describes the standard as providing the minimum requirements for energy-efficient design of most buildings, except low-rise residential buildings. It offers in detail the minimum energy-efficient requirements for designing construction of new buildings and their systems, new portions of buildings and their systems, and new systems and equipment in existing buildings, as well as criteria for determining compliance with these requirements. It is an indispensable reference for engineers and other professionals involved in design of buildings and building systems. Architecture 2030 is a nonprofit 501c3 research organization. Architecture 2030 issued the 2030 Challenge, which was adopted by the American Institute of Architects and forms the basis of the AIA's 2030 commitment. Architecture 2030 is responsible for numerous programs and initiatives, as you can see here. The 2030 Challenge being perhaps what they are most well known for. According to their website, Architecture 2030 issued the 2030 Challenge, asking the global architecture and building community to adopt the following targets. All new buildings, developments, and major renovations shall be designed to meet a fossil fuel GHG-emitting energy consumption performance standard of 70% below the regional or country average median for that building type. At a minimum, an equal amount of existing building area shall be renovated annually to meet a fossil fuel GHG-emitting energy consumption performance standard of 70% of the regional average/median for that building type. The fossil fuel reduction standard for all new buildings and major renovations shall be increased to 80% in 2020, 90% in 2025, and carbon neutral in 2030. aka using no fossil fuel GHG-emitting energy to operate. Back to our metric. Now we better understand what this energy cost mean visualization is benchmarked against, which is measured in cost per area per year, or energy use intensity per area per year, and you can toggle between these on the Insight interface. We've seen how easily we can create an energy model from our conceptual mass and review it on Insight's web interface. Coming back to our Revit model, the first thing we might be interested in doing is a lighting analysis. There are a number of different types that we can run, from a custom luminance analysis to specific credits you might need to provide documentation for if you're pursuing LEED or WELL certifications for your project. Once you've set that up and click Go, you might wind up with something that looks like the image on the right. I've hidden the roof in this 3D view of my conceptual mass as the roof shows up nearly entirely blown out. Now we have a clearer view of the typical floor lighting analysis. We can see quite quickly the lux is high along the southern and eastern edges of the floor plates. Lux is the SI-derived unit of illuminance and luminous emittance, measuring luminous flux per unit area. Translation: This is the measure of the intensity as perceived by the human eye of light that hits or passes through a surface. To help make sure we don't have too much intensity in a specific area, we might consider adding exterior shades in key locations of the building exterior or other design moves to facilitate this. The results summary is quite helpful, especially to see instantly if you are meeting or not meeting the criteria you have set up for yourself. Next up, let's take a look at the solar analysis tool. In terms of analysis type, we will select between custom and solar energy, which provides an estimate of the photovoltaic production for the year. For this concept mass, I've selected to run it on all mass surfaces. The result type I've left as cumulative insolation. Insolation is the amount of solar radiation reaching a given area. The results in some ways tell a similar story of what we learned with the lighting analysis, but the information is different and serves a different purpose. While I've run this analysis on the full mass, you would likely constrain your analysis to areas you would consider putting PV. The roof, if not dedicated for mechanical or a roof garden, is a common spot and clearly the best spot according to this analysis. Another item you might want to visualize is the sun path of the sun over the course of the year. This is easier than you might think. At the bottom of the Revit window between the visual style icon and the shadows toggle, you can select to turn on these sun paths to create a diagram similar to the one pictured here. The third item, heating and cooling, also tells an interesting story about the HVAC loads that a building might encounter. If we click the heating and cooling button, it will provide us a breakdown of loads by component and spit out a report such as this one that identifies items such as peak cooling and peak heating loads as well as total building area and volume. Back in the Insight web interface, we can also easily visualize the same analyses we've been performing in Revit. Click on the Visualize icon in the top right and then select Heating Loads. And you will see a visualization of areas that require more heating than others. I should note, this sort of analysis does start to make more sense at the point you have a better understanding of interior volumes of space and rooms. Similarly, we can select cooling and see what areas have the highest loads from that angle. So, we can see just how easy it is to get some meaningful feedback early on in the design process using this tool. You might be thinking to yourself, sure, but there must be a ton of assumptions baked into seeing a single EUI number spit out of such a simple conceptual mass. That's true, but those factors can be easily adjusted and fine-tuned through a number of options in the back end. I think, though, the main takeaway here is that some of the tasks that used to take numerous different softwares and expert energy modelers are now becoming increasingly integrated to softwares we already use for production, and there is a much lower threshold of entry. The sort of tweaks and understandings needed to validate complex models will still benefit greatly from involving those experts. But at this point, everyone should have some fun experimenting with what different design moves accomplish or cost you, so to speak, in terms of energy, daylighting, and needs for HVAC. If you're curious to learn more, please check out these videos, the Autodesk webinar by Jad and Ian, and the LinkedIn Learning course by Jim Cohen. These videos are both rather long, so it is not mandatory to watch these, but feel free to peruse these or come back to them later in the semester as a reference if you are thinking about doing an in-depth energy analysis as part of your final deliverable for this class. How about utilizing Rhino or Grasshopper to perform an energy analysis? DIVA offers some robust tools that allow for environmental analysis of Rhino models. Their website notes, DIVA is a highly optimized daylighting and energy modeling plugin for Rhino. The plugin was initially developed at the Graduate School of Design at Harvard and is now distributed and developed by Solemna LLC. DIVA for Rhino allows users to carry out a series of environmental performance evaluations of individual buildings and urban landscapes. This includes radiation maps and photorealistic renderings, annual and individual time-step glare analysis, LEED and CHPS daylighting compliance, sun-path diagrams and shadows, thermal zone energy and load calculations, and daylight simulations. If you are interested in setting up your Rhino model to run daylight simulations using DIVA, please check out this handy PDF guide that describes how to set it up properly. Additionally, if you are thinking about setting up some visualizations, daylight autonomy studies, or sun path diagrams, feel free to check out these video links. These are not required to be watched, but I recommend them if you are thinking about trying to use any of these on your studio project or your case studies. If you're looking for something which is free and open source for everyone, not just educators and students, you should check out Ladybug and its associated tools. Its website describes itself as a collection of free computer applications that support environmental design and education. Of all the available environmental design software packages, Ladybug Tools is among the most comprehensive. Part of the suite of Ladybug tools includes Honeybee, Butterfly, and Dragonfly. Honeybee creates, runs, and visualizes daylight simulations using Radiance, energy models using OpenStudio, and envelope heat flow using Therm. Butterfly is a plugin and a Python library to create and run advanced computational fluid dynamics simulations using OpenFOAM. Dragonfly models large-scale climate phenomena such as urban heat islands, climate change, and local climate factors such as topography. Here is a graphic illustrating how a lot of those different plugins work together and allow for analysis of a variety of items such as glare, daylight, annual daylight, U values, sizing of HVAC systems, airflow analysis, energy modeling, and environmental analysis. You can utilize the software to create things such as psychometric charts, temperature visualization for a specific site for time of day against the month of the year, or a windrose diagram. If you are interested in getting rolling with Ladybug and Honeybee, these free tutorial videos on YouTube are a great way to dive in. And now, on to the last topic. Don't worry, we're just about done with the lecture. Performance-based design. That is also a broad topic, just as environmental analysis is. And we're not going to go into the weeds too much here. Just cover a few definitions and some context you might encounter the term. To begin with, performance-based design is usually contrasted with prescriptive design. It is common to come across these terms in both building code and specifications. In terms of specs, an architect might prescriptively call out specific products and list those approved manufacturers by name. No other products would be acceptable other than those. In a performance-based spec, one would describe the qualities of a particular product that would leave the exact product open-ended. For example, one might call out the acceptable level of flame spread rating for a type of waterproofing, or the minimum amount of recycled content for a piece of furniture, but not prescriptively list only a few approved providers. Similarly, when it comes to building codes, many are prescriptive, but the energy code is a good example where multiple paths of compliance are available to design teams. One might show compliance by prescriptively following a checklist, or, alternatively, one might show compliance pursuing the performance path by utilizing an approved energy modeling software such as the three we touched upon earlier. A performance-based design approach to code compliance is often taken with high-rise buildings for their seismic design. Building codes often allow for this non-prescriptive path for these complex structures. If you're interested in pushing the envelope of your project structure with a performance-based design approach, you might check out the Carumba plugin for Grasshopper. Download a trial version, but unfortunately the student and educator license is not free, though it is considerably less expensive than the professional license. Carumba 3D is a parametric engineering tool which provides accurate analyses of space trusses, frames, and shells. Check out these Carumba videos if you are interested in using real-time feedback on structural performance as a design tool. That concludes the Week 10 lecture. Here's a snapshot of the homework assignment. The first question asks for 3 conceptual masses of your studio project or case study be created, and a lighting analysis of those 3 schemes be run using the Insight plugin for Revit. The second question asks that a similar analysis be performed on those same 3 conceptual masses in Rhino. You could start with either question 1 or 2 and then export those masses out to use that same geometry in other software, or recreate it from scratch. It's up to you. The goal of asking you to utilize both programs is to illustrate it is possible to achieve this in a variety of software. Question 3 asks you to reflect on which of those tools, after you use them, seem to work best for you, and why. Question 4 is to get everyone thinking about what they might want to produce as a final deliverable for this class. I can't believe we're already near the end of the semester, so I think it's good to start thinking about this. It could be related to taking a more in-depth dive with an environmental analysis, or something else entirely, even something we haven't yet covered in the course but you're passionate about. But generally it should be related to the overall topic of advanced digital design. Question 5, I ask that you read a few short articles and watch a few minutes of another lecture that highlight a variety of viewpoints as they pertain to sustainable design in the context of the architectural profession. I hope reading through these perspectives helps provide a framework that wards against anyone developing a myopic vision about what is important in their design projects and any single shiny new tool. Please digest and reflect on these positions, and then develop your own. I would anticipate this would involve at least a paragraph or two to address the questions asked. Please refer to Blackboard for further details.